Hello, I'm Sam, and in this video I'll be showing how I did this openEMS simulation of a Rotman lens in Blender. This won't be a step-by-step tutorial, but just to show you my workflow and the tools I use to create this, and how I first of all made the geometry in Blender and then imported to openEMS and then got the results back in Blender to do this animation. I was inspired to do this work after seeing a few posts on LinkedIn. First one from Lucas Henkel and other people as well about the Rotman lens. Now Lucas has done this in Elmer. Elmer is a finite element solver, whereas I'm going to be using openEMS, which is an FTTD solver. So it's a bit different. I'll also be using other open source and free tools for this. So I'm going to be using Inkscape, and I'm going to be using Octave for openEMS and Paraview just to visualize the results. So all the tools that I'll be using are free and open source for this demo. So first step is to actually describe what is a Rotman lens. This is a tweet from Andrew Beck, which I'm not sure if he designed this or not. But anyway, the way the antenna works is that it's a way of controlling the beam in a phased array antenna. So what you see here is the Rotman lens in the center and the active ports on the left. And depending on which port you activate, this allows you to control the beam, the angle of the beam that will be created in this phased array here. Now, there's a few articles on LinkedIn and a few images that describe how these Rotman lenses work. I'm not really familiar with it, but anyway, the first step in our simulation is to get the model of a Rotman lens. Now, I came across an article from the University of Windsor by these authors, and it shows the design of a 77 gigahertz Rotman lens. So, and they give you an actual image of this Rotman lens. So first of all let's take this image and let's just screen capture this for now, and for that, and then let's go to Inkscape. Just paste it here, and with Inkscape you can actually trace this image to generate a vector image, which then we can import into Blender. So first of all if you haven't got you need to get activate the trace bitmap panel, and then you need to play with the threshold here to actually get the image to show. And so this is what the preview of the traced image is. So if we apply this now and just delete our first image, and if you zoom in, and you can see now this is actually a vector image which we can then import to Blender. Let's just clean it up a little bit and let's remove some of these parts of it. So remove this arrow. Now that's it. This is now our antenna. Don't worry about the dimensions of it, because we could set this up in Blender. So go ahead and save your file. So I'm going to call it Rotman Lens. I already made one, so I'm going to call it 2. And then now we can import it into Blender. Okay, so let's now import our antenna into Blender. I've got a brand new scene. I'm going to delete everything and File, Import SVG. And this is where it is, Rotman Lens 2, import that. And it's now been imported, but it's very small. You can't see it, you have to zoom in. And so first of all, let's scale this by a factor of 10. And it's gone all the way there. Let's change the origin and make the origin of this object is now here at the world origin. I want to center it right there. So I'm going to go right click, set origin to volume, and then Alt G brings it back into the center. Now, if we go into edit mode, this is actually a curve. So we need to convert this to a mesh so that then we can export it as an STL file. And to convert it to a mesh, you just go right click, convert to mesh. And now this is what we have. And if you go into edit mode, you see all this mess. We need to clean this up. So select everything and go to mesh, clean up, limited, dissolve. And now we have a cleaner mesh for this. One more step is we want to merge some of the vertices that might be very close to each other or overlap with each other. So just select everything, hit M on your keyboard, merge by distance, and it will tell you here at the bottom that 113 vertices have been removed. Anyway, so this is our lens now. Now, I did mention in the beginning about the scale and dimensions, and so now we can do this here in Blender. If you press N on your keyboard, you'll see the dimensions of this. Now, here dimensions are in Blender's dimensions are in meters, but let's ignore the meters for now, because when we export it, we can change the scale of it. But let's go back to our paper which mentions the dimensions of the of the antenna. So it's 15.6 and 19.7. So let's compare what we have here. So in the Y direction, it's 15.6 and 19.7. So this is 0.6 and 19.7. So this is now our antenna. If we just compare it side by side with what we see here, I think it looks identical, and that should be good enough for now. And so now let's apply the scale. And so now the scale is 1, and this is the dimension. So as I mentioned, ignore the meters unit for now. Assume this has no units. Okay, so now we've got our antenna, our lens, sorry. The next thing we need to do is to define the substrate and the port and the ground plane and all of that. So let's set this up here. First of all, let's name our object. So let's call this Rotman here. Let's call this openEMS simulation. This is our collection. So let's first of all add our ground plane. Now, if you have a look at the paper, we don't need to follow the exact dimensions in the paper, but it tells you that the substrate is 200 micron and the copper thickness is 1.5 micrometers. So as this is just a rough guide, we don't really need to follow these numbers, but let's just try to set them up. So first of all is we need to give this some thickness. So let's extrude this by a little bit. And so now this has been extruded, and the paper said it's 1.5 microns. I'm going to assume that is standard PCB copper, 35 microns. So this is then going to be, that's going to be the thickness of it. In fact, let's also remove the material so we can see this a bit better. And I'm going to change my viewport properties. I'm using HardOps, which gives you many options and shortcuts and macros to speed up your workflow in Blender. And let's just set the scene color to random, so that if we have other objects, such as, for example, we have a cube, we can now see them clearly. We can distinguish between them. So we need to add a copper plane for this. So let's just basically go add a plane, and let's just scale this for now. So we need to scale this in the X. Let's go to edit mode, bring this down, bring this over here, and let's bring this over here as well, and let's bring this right up. It doesn't have to be exact. And we also need to bring this down by 200 microns, so we can basically do it here. So that's going to be minus 0.2. Okay, and let's give this some thickness as well. So let's go to edit mode and give it some thickness, and also let's say 0.35 as well. Now, of course, the distance is not going to be 200 micron, so this is from here to here. You can see that because we've added the thickness, and just simply to do that we need to subtract it by the thickness of this, so 35, and now this should be 200 microns or so. Okay, so that's our ground plane, and let's call this G&D plane. Okay, so and now the next thing is we need to add the substrate, which is essentially, I'm going to just copy this object and just extrude it such that it fits between the two parts, the lens and the ground plane. I'm going to enable snapping to face, so snap to face, and that's snapped right here. And also let's grab this up and right here, so there we go. Now, one thing in openEMS is that although you can see the substrate and the copper is sitting exactly on top of each other, they're snapped to each other. Sometimes I prefer to have them a bit of overlap, because that depends on the mesh that it makes the meshing easier. And of course we can change the priorities in openEMS such that we give priority to the copper over the substrate. So let's bring in X-ray mode, and that's the one here. Go back and let's bring this down. So there's a bit of overlap. Okay. In fact, the scale is too big for Blender. If you work with large dimensions, it can be difficult to navigate. So I'm just going to actually scale it back down, like so. All right, so that makes it easier. I'm going to apply all the scales and the transformations, and so now we have our This is going to be our substrate. There we go. And that's our ground plane. What you could do is make Blender review the names, so then you can. So here we've got ground plane. In fact, things have moved a little bit, so let's bring it up like so. Apply all transformations again. Okay, and this is going to be our substrate, and in fact they show on top of each other. That's not a good idea. Okay, remove all of that. Okay, so now we've got our substrate and the lens. Next step is to add the ports and the E-field dump boxes. Okay, the next step now is to add ports. So I'm going to assume that this trace here, or this stub here is where I'm going to send in my signals. So I'm going to have my active port here. I'm just going to hide the substrate for a second. So I'm going to have my active port. I want it to be here, and all of these other traces or stubs, I want to assign a dummy port to them, and that is because all the waves that will be traveling, I want them to be absorbed. We could define it as a lumped element or as a inactive port. I think that both solutions would work. So let's go ahead and do that, and let's first of all just add in a cube, and that would represent our port. So what I want to do is I want to bring this cube I want to size it such that it fits just between the lens trace and the ground substrate, and I also want it to be overlapped a little bit, so I don't want it to be exactly snapped, just because when I do the meshing, I don't know exactly at this, because it's just a quick guide, the mesh line might not actually cut right at this exact point here. So it's best to have some overlap between the ports and the copper traces. So let me just size this a bit more, and let me just bring it here. Go and go to edit mode. So bring this up, gonna have some overlap, turn X-ray mode, and same thing with here. Just bring it down a little bit so we have a bit of overlap, and let's shrink it in the Y a little bit, and perhaps let's just make this a bit longer. So that is our first port, and I'm gonna call this active port and put it under openEMS collection. And so next thing to do is just simply duplicating this port for all of these traces and stuff. So let's go ahead and do that, and I'm just going to skip through the video. Okay, so now I've created all the ports here. I've called them dummy ports, and the best thing to do is to select all the ports and move them to their own collection, dummy ports, and let's move this collection to under openEMS, because that would make it easier when we export those. So that's what we have now. We've got all of these ports, so let's select them all. Those are the ports, the dummy ports, and this is the only active port. And finally now is we need to define our E-field dump box. So what I do is I just want to take the substrate, duplicate that, call it E-field dump, and I basically want to capture the E-field not just in between but also slightly above and below the copper. So I'm going to scale this so. Turn on X-ray mode, and I could just have it as a plane, which would make the files that openEMS would generate, their sizes would be very small, but it might not create the best visualization. So I like to capture all the field around the lens and also in between as well, just to get the visualizations to be better. It does mean that the file sizes will be quite large, so you need some space on your hard drive. So now we've defined all the geometries we need, and now it's time to export it to openEMS. Okay, so just to give you a preview of what the code in openEMS looks like and what we need to do to export the files from Blender. So in openEMS, it allows you to there's a function called import STL, and you can use this function to import, for example, the traces, the ground planes, and the substrate. So you see here, I do have my Rotman Lens as an STL file. It has a transform and a scale value, and it's assigned a metal property to it. Whereas for the FR4 substrate.STL, it's assigned a material, an FR4 material, and it's got a epsilon value, a permittivity value that you can assign to it. But when it comes to the dump boxes and the ports, we cannot export those or import them as STL files in openEMS, you have to specify the coordinates. So in openEMS, it assumes that the dump boxes and the cubes are, and the ports are cubes, and you just need to specify the coordinates of the cube's corners, just 2 corners, the maximum and the minimum corners. So that's what we need to do now in Blender, is to first of all export our meshes as STL files, and then we need to somehow get the coordinates of the ports and the E-field dump boxes. Okay, so now we're back in Blender and we need to export our meshes as STL files. So let's go ahead and do that first. So first of all, let me export the Rotman Lens. Now, one comment about the scale here. So if you look at the scales for this object, you'll notice that it's 1.97 because I scaled it down at the beginning of the video. Now, as I mentioned, ignore the M here for meters for now and assume this number has no units for it. So if it's 1.97, I know that from the paper that this should be 19.7 millimeters. So when we export this mesh, we need to multiply the dimensions by 10, and that's where, when we go to File, Export as STL, here we have a few options where we can set the scale here, and we do make that 10. So then we have our units in multimeters, and so we selected the Rotman Lens. So let me call this Rotman Lens, and make sure you select ASCII, selection only, and apply modifiers. And we need to do this for each object. So next one is the substrate, and similar thing, File, Export, STL, and all these settings have been saved from the previous export. So let's call this substrate. And finally the ground plane right under there, so let's export that as well. Ground plane. Okay, and now let me just hide the ground plane, and let's first of all hide the substrate, not the ground plane. Let's bring our E-field dump box. So now we need to, as I mentioned, we can't export this as STL, so we need to get the coordinates. So if I go to local view mode, so I'm only viewing the dump box, and if I go to edit mode, I basically need to get the coordinates of these vertices of this cube. So yeah, I'm going to select this one, and I want this one, so it needs to be 2 extreme corners. So in Blender, if you go to item here, Blender will give you the coordinates. It will be actually in local mode when you first click on this, but make sure you select global mode, so then the coordinates are in global space, not local space. And now it's a manual process. You need to basically copy each number, Control C, go to openEMS, and come here and paste this, and I've set the multiplier here by 10, so e to the power 10 to the power 1, so that means it's multiplied by 10. So basically you need to go to each of these coordinates, Control C, Control V, and bring it back here. So I've done this for this dump box, and the same thing we need to do for the ports. So let me hide the E-field. So the active port as well, we need to get the coordinates of these 2 extreme corners. But as you already kind of can see, where this is going is that I've got so many of these ports. If I'm going to copy this manually, I'll spend a long time doing it. So we need to find a smarter way of actually getting these numbers from Blender into openEMS. And so now we need to use Python, and we need to write a script in Blender to export the coordinates of all these dummy ports. So in Blender, if you go under the scripting tab, you can add your code here. So you would basically create a new code, import BPY, Blender Python, import OS, and then you would start typing your code here to export the coordinates. Now I've already done this. I've already written the code, and you can copy this. So how this works is we need to generate a file. I'm going to call it dummyports.m. And so in this file, I'll be writing all the coordinates of these dummy ports. So the way this code works is, first of all, we set the directory of the output, which is going to be the same as where the file location is. And then we create the dummy port file. And this code works on the objects that you select. So I can select all the dummy ports under this collection. That's why I put them in the collection in the first place, so that I could select all of these ports. So I've got all the ports selected. So then this command will, this Python code here will then store all the objects that are selected, bpy.context dot selected objects, and then I've got a unit multiplier because here the units will be, I want them to be in millimeters. And so then you have a for loop which then goes through all the selected objects. First of all, it stores the coordinates, the matrix world coordinates, because if you just get the coordinates of the vertices, they will be in local space. You need to transfer them to the global space. And so that's what it does. Now for the vertices that you need to select, I'm selecting vertex number 0 and number 7, because in the cube we need to select, this is the port here, I need to select, I mean just local mode, I need to select this vertex and this vertex, or this vertex or that vertex. And to get the index of which vertices that you need to choose, in Blender, when you are in edit mode, you can go to enable indices, and now it will tell you which indices that you, for each of these vertices. So this is index vertex number 7, and this is vertex number 0. So these are the extreme corners of this port, and that's what I'm doing here, 0 and 7, or you could use 3 and 4, 5 and 2. And so then this is what it does, it just takes the coordinates and writes them in a text file. So then if we run this code, it runs successfully with no errors, and we have a look at the output. Here's the output. It only generated one port because we had only one selected. Go back to local mode and make sure we've selected all of them. Run this code again, and now we should see the coordinates of all of these ports from dummy port 2 all the way to 23. One thing also in the code, you notice that I start from index I plus 2, because in Octave you start from 1, and because number 1 is already used for the active port, that's why then I start from number 2. And so that's how the code works. And now we can go back to Octave to then finish our openEMS code and start running the simulation. Okay, so I'll give you a quick overview of the code so far that I have for this in Octave. So I generally use just the templates from the examples from openEMS, and I just modify them based on the geometry that I have. So here I've set the center frequency to 70 gigahertz with 5 gigahertz 20 dB corner frequency, so the bandwidth is 10 gigahertz, and I'm using a epsilon value of 8. I'm not using kappa or the loss at this time, so this has no value. Airspace, there is how much space you need to add. Once you define the mesh, you need to add space for air, and I'm just using 1 millimeter extra space. And then you set up the FDD parameters, the number of time steps for this. The longer this number is, the higher this number is, the longer your simulation will run for, and you capture more of your simulation. I'm not sure what minimum decrement is. It might be to do with the end criteria, or at which point the simulation stops, or maybe not. Gauss excite. Now the boundary conditions, I generally use MU. I haven't experimented with others like the PMC, which is, or the PML, the perfectly matched layer. Mirror works absolutely fine for me. And here is now the very important bit where you define the mesh, and that's where you're going to spend most of your time playing with the mesh until you get your simulation working. So I've actually experimented with this, and I came up with these values that seem to get the simulation working. I had issues with some values first, but this is now what seems to be working for this. So this is where you're going to spend most of your time, is when you define the mesh for this. And then you import all the geometries as STLs, and then you define your dump boxes and the ports as well. So with the ports, because we did our script, so we're just importing the script here, and this is our active port. And that's pretty much it. So that's an overview of the code. As I said, this is just taken, I just took a template, the example template, and just modified it. So now we can run this code. Before we run it, we need to add our openEMS path where openEMS is installed. So then you just run the simulation, change directory, and you need to answer yes to this question. And now the simulation is running. First of all, you'll get this CSX CAD where you can preview your mesh and see if the mesh lines intersect the ports, for example, and the copper and the substrate. So this is, as I said, where you're going to spend a lot of time trying to make sure you get your mesh that works good for this for your geometry. And you can sort of use all of these features here to kind of troubleshoot and check what's going on. So once you're happy with this, you can, as you close this, the simulation will begin, and this will take some time, so I'll skip through the video here. The simulation is now finished, and it took just under 20 minutes on my machine. And the results so far, we can see that you get a plot of the S parameters, S11, and you can see here that around 70 gigahertz, just above, or 71, it's actually really good, minus 45. And this is sort of the plot time domain waveform. You see we fire our Gaussian pulse, and then but we do have a bit of reflections coming back into the port. And then the next step is to go to Paraview and to actually view the simulation result. So in Paraview, when you start Paraview, you can load up your files. And so right here I've got the edump thing, so I've got about 413 time steps. So if I go, for example, start at if you run this, it'll be a bit slow because the files are quite large. So in fact, the file dimensions are around 40 megabytes, so quite large. So it will take time for the results to show. We need to obviously scale this properly. So let's scale this to 0.25, and you see we start seeing our first pulse coming through from the port here. See, this is where the signal is being fired. It does fire from all angles, so you can see here actually it goes from where the trace is, but also goes behind the trace, and you can see now signals start to appear slowly, and there it is. The signals are going actually behind the port, are reflecting and bouncing off the PCB edge. Of course, you can fix this depending on the port that you define, but I think it's fine for what we do. Now, this is obviously viewing the E-box dump from the top. I would like to see, so this is the E field just above the PCB. I think for first visualizations, it's good just to see the E field inside the PCB, because that's where the waveforms are. So what I've done is I've set up a clip here, and let me just hide this. So now I can see the actual E field inside the PCB here. And I think this is a better image now. We can see how the waveforms are formed, the waves travel, and maybe we can adjust the scale. Let's go to 0.5 maximum, and let's jump in time, go to 200, and there you go. You can start to see how this lens works. So the input signal comes here, and then it spreads, and then goes to the output traces here. And theoretically, what should happen is all these dummy ports, so we should see no reflections, or all the waves should be absorbed. And perhaps here, this one's all these waves, they're traveling mostly here and not much so on these traces that are close to the input. So far things looks okay. We start now to see some standing waves that are forming, probably to the mismatch. It could be due to the mesh or the geometry itself, the dielectric properties that we set. But so far it's looking okay, and you can see here these waves are traveling, no standing waves so far. You can see clearly the standing waves are being generated here and here as well at the bottom. And if we advance perhaps up to 300, okay, so this is where things start to collapse. Maybe go to 275. So you can see now the effect of these standing waves as the waves reflect back from these dummy ports back into, and they start to sort of destroy all these wavefronts that we see here. Although most of our signal, the energy that we put in, has actually passed and went through these dummy ports. You can see now there's no standing waves that are being generated here, which is good. And now we can see the waves that are being reflected back into our port here. You can see they're traveling back. But so far I think this looks okay. And of course we don't have the phased array, so we don't actually know how the beam angle is going to be. And the next step that we could do, obviously this will make the simulation even longer and more complicated. Okay, so now that we have our results, we can export it into Blender. But before I do that, I generally like to add a filter here, the warp by vector filter, and that is because it gives this nice 3D effect, which looks cooler, I think, when you view it in Blender. So if we get in a bit closer here, you can see if I just get this, There we go. So it just looks better, I think, when we use this filter. So then once we import the data into Blender, it looks a bit better and even can run faster actually. So I just use the representation by points. And to export it into Blender, you need to do it as an X3D format. So you go to Export Scene, and then let's call this 250 and as an X3D file. And let's save it. You don't need to export that. So if you open a new Blender scene, so the brand new Blender scene, delete everything and go to File, Import X3D. If this option is not available, I believe you need to go to your add-ons and enable it here. So X3D, yeah, make sure this is enabled if you don't see that option. So File, Import X3D, and locate it right here. And so I import that. So there it is. Basically, it imports the entire scene that was generated in Paraview, even the lights and the camera. So if you have a look here in this panel, you can see what's been imported. It's the lights. This is shape point set is what actually is the data that we're interested in. So what I'm going to do is I'm going to delete everything except that. And I'm going to just increase the scale by about 100. And so there you go. This is our data that's been imported from Paraview. Let me just rotate this by 90 degrees. And so this is our actual data. You can see here, got all the data points, and we've got about 413,000 vertices here. So obviously this is quite a large number even for Blender. So we will have to do some processing on this. For example, remove the points that are close to 0, only keep the ones that actually are above 0 and have these nice bumps to them. So this is where now we can use geometry nodes in Blender to process this. Okay, so now let's use geometry nodes to make some changes to this and filter out some of the points that are close to 0, and just to simplify it a little bit. So let's start in with geometry nodes. First of all, let's apply all the scale and all transformations, and let's create a new object, and then let's use geometry nodes on this new object instead of the original one. So let me hide the original one. So this is our cube, and I'm going to import our data object, which is right here. Now, first of all, I want to erase the points that are close to 0. So what I'm going to do is let's separate X, Y, Z. Let's get the position first. Position, separate X, Y, Z, and then let's go with delete geometry. Obviously, this is going to delete everything. So we want the ones to be closer to 0. Let's pin this as well. So I'm going to need the math, a compare node, and equal, and this is set, and plug in the result here. So this is what happens now. You say A is equal to, actually put it in A, and then we can now adjust the epsilon value a little bit so that we could clear out the points that are close to 0. There we go. And the next thing is we want to instance a sphere or an object on these points, because we can't render those as they are. We could do it with cycles, but we want to, with Eevee, we can't do that. So we need to use instance on points. Instance on points, and let's choose an object that we want. So let's go in with a cube, and let's instance that. So obviously we have many cubes now, so we won't need to adjust the scale of this. Let's do it like that. So now we have all of these cubes. Let's hide in the shadow. That speeds things up a little bit. So in fact, what I do next is that I subdivide this cube to make it look as sphere. I could use a sphere object, subdivision surface here, but I find that if I use sphere, it has too many. I can't control the resolution of it, so it might slow Blender down. So what you could do is that during the viewport, you could disable this, and when you render it, then you could enable the subdivision surface. So, and let's add shade this smooth, set shade smooth. There we go. So now we have our points as spheres or subdivided cubes. Next, what we could do is, I'd like the points that are closer to 0 to have a smaller scale than the ones that are on the top, or the ones that are on the top with the highest amplitude should be much larger than the ones that are on the bottom. So to do that, we need to get the position of each of these points and normalize the position of the point. So we have the Z position here. Let's get the absolute value of this. Let's get in the math node and let's set this to absolute so that we capture both the negative ones as well. And then what we could do next is we use the statistics node, and what I would want is the maximum. I want to basically normalize this. I could use a map range node as well. You could do it that way. But what I generally do is I then basically divide the position of each point by the maximum just to normalize it to 1. So this is divide, so this goes down here, and then we get the position of this. And so next what we could do now is we've essentially normalized this. So this could go directly into scale, but you can see here some of the points are small, some of them are large. We could go into a map range now, where we know our minimum value is 0, maximum is 1. And so now we could actually decrease this. And you can see already that points that are close to 0 are very small, and the ones on the top are quite large. You could obviously play with this however you like. So I could increase the small ones a little bit. I think I generally go with 0.5 and perhaps 0.3 or 0.2. That looks better now. So I think that's all there is to it now. Next thing is we need to set the material for this. What I also want to do is I want to store the normalized position, so then I could change the color. So the points also that are lower here have sort of a different color than the ones that are on the top. So let me store and just call this normalized. And I would want to store this value here. So that's let's call this openEMS. And now we need to set the material. Set material. Let's create a new material and let's call this openEMS material. openEMS material. Okay, so let's go to our shader editor now, and we can see here in our geometry panels we have the position normalized data. So let's bring in our attribute and get our point here. Let's go to shader, and let's first of all, with Node Wrangler, perhaps we could see something. We don't see something yet. In fact, just to confirm that we've got the data. Oh, so what we need to store this in, not on the points domain, we need to store this on the instances. So now we should be able to see the columns. So previously it was on point. We don't see it because our domain is instances. And so there we go. And so now back to our shader editor here, and this should be instancer. And now we can start to see that yes, our attribute is working. So next thing we could do is we could go to map range, and I generally like to use black body here, so I can set the temperature of it. So we bring this here and this right there. So we start from 0 to 1, and I want to start from 5,000 up to, let's say, 10,000. And of course we need to enable that. So we start to see something here. There we go. Let's maybe bring this down to 5,000, and we start from 1,000 here. So you can see the ones that are red are on the bottom and white, which are very hot, on the top. Maybe I would like to have it the other way around. Up to you how you want to visualize it. And I also like to set the emission as well. So what you could do is get this into emission strength and get the color from black body as well. Put it here and maybe put in a math node so you can control the amount of emission. So you can see here, I can bring it down to 0 and it gets brighter. Or maybe perhaps we could bring this down a bit more, or bring this one down to 0, increase that. So you get the idea. Of course, this is only for one frame. We need to now export all the frames from Paraview and then import them into Blender and apply the geometry nodes. So the next thing we'll do is now write a few scripts to do that. And so now we want to export in Paraview multiple scenes. So to do that, you can do it via Python. So in Paraview, go to Tools, Python Script Editor. And I did write this Python code here. Very simple. All it does, you set the directory, the number of frames that you want to export. So I got 10 frames here, or you could export all of those frames. And then just a for loop that says for each frame, export it as X3D file, and then go to the next frame and so on. So in fact, this should be string I. There you go. So that's how I do it in Paraview. So if you run this script, it will take some time, and you'll see here as it exports, it goes through the frames, the number of frames that you say. So 10 frames. So from 200, it should stop at 210. And here are the files that have been exported. They start from 0 all the way to 9. And now in Blender, we just need to do the reverse. We need to import these X3D files, filter them out, and only get the data. So back to our Blender scene. Let's go to scripting, and let's call this import X3D. Now I've already have a script written for it. All you have to do is specify the directory of where you stored the X3D files, the frame range, and then for every X3D file you import it. And then what I do is, if you remember that when we imported the X3D file, it was the shape point set object that contained our data, and there were also cameras and lights that were imported as well. So what this script does, it deletes everything that's not the data. So it deletes the lights, the camera. You might have curves and other types of data sets that might be imported. So when you import this, let me first hide everything in our scene so that we know this script works. And let me just do a few changes here. Sometimes I do an offset and the namings depending on where I started my frame number. But let's run this. It will take some time. Okay, so after a few seconds, this has been imported. Also, in Blender, you could view it does print a message for every frame that it imports, so you could make sure, because it might seem that your PC is stuck, but in fact, it's importing the files. So we've got all our files now here. Let's go back to layout, and let's move all of these objects that were imported. Let's move them to their own collection. Move to new collection. Let's call this openEMS. So now what we need to do is we need to modify our geometry node setup to account for all of these data frames. So what we need to do is for each frame in Blender, go to timeline. For each frame in Blender, we want to cycle between these data points that we've got and apply the geometry node setup that we created. So that's what we're going to do next. Okay, so now what we want to do, let's hide this collection and let's just add in an object. And I'm going to make a new panel here and go to geometry nodes, and let's add the collection, the geometry node setup that we used previously. So now instead of importing just one object, we want to import a collection. So let's bring in collection info, and that's going to be openEMS collection. And so now what we want to do, so if we just view this directly, we see all of these data points together combined. We want to, for each frame here, we want to separate. We only want to take one. So what we could do is we need to use the separate geometry node, and then for the selection we want to select each of these data points for each frame. So at frame 1, I want to select ET1, frame 2, ET2. So we need to get the scene time, and then we need to then compare that to the index. So let's say equal and integer. So let's get the frame and let's get in the index here. And let's just view this now. We do see something going on. And you want to separate children. Oh, it's the instances here. Okay, there we go. That's better. So now you can see that. Let me just pin this. There we go. So for these first 10 frames, you see that we're actually cycling between all the data points. And so all we have to do now is just plug in this to here and hide our view. And okay, this didn't work. Or let's make sure. Let's view this, delete geometry. Oh, we need to realize instances, because at the moment, at this point here, we're actually generating instances, whereas this is expecting points. So we need to realize the instances and convert it to a mesh. And so there we go now. Let's hide this. And that's now working as you would expect. So let's just make this to 10 frames. And let's go to our shader view. And so now if we give this, it's only the 10 frames, but you get the idea. And so that's been this video tutorial, or guide I should say. I hope you found it useful, and stay tuned and subscribe for more videos like these. Thank you very much.